Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And as I alluded to in the daily weather update, it's a technical title for a reasonably simple concept. And I remember first learning this, actually may have been in high school, that one of my mentors from Penn State that I met before I even went to college there talked to me about this. But it's called the downward transfer of horizontal momentum. And all it is there are ways to get the stronger winds that many times exist up there to mix down to the ground. And so that's what we're going to talk about today, is the mechanism behind that. So let us go on ahead and take a look at something called a skew-T chart. Now I've shown this before, but for those of you that are new, this is the chart that a lot of meteorologists use to plot soundings. So when various weather stations send up weather balloons twice a day, then it takes readings, the balloon does, well actually the instrumentation attached to the balloon takes readings as it goes up in terms of temperature and dew point, and then by tracking the balloon and the instrumentation, you can then tell or calculate what the winds are doing, different directions, different speeds as you go up through the atmosphere. So what you're looking at here, and I'm going to take myself out of the picture so you can see the entire thing, okay? So got to click right up here real quick. There we go. So these are levels of constant pressure. So in other words, there's the 1,000 millibar level, and then in increments of 50 all the way up to 600. Now, if you were to look at an entire skew-T chart, it would go all the way up to about 100 millibars, okay? But there was no need to do that in this case because that part of the atmosphere is irrelevant for what we're talking about. Then you have lines of equal temperature, or isotherms, and they are skewed, hence the name skew-T chart, okay? So 0 degrees Celsius, which of course is 32 Fahrenheit, is this line here. Then it goes up 5, another 5, another 5, another 5, up to 20 degrees Celsius. And while I'm at it, and I think I may have mentioned this a long time ago, but I came up with, for me, a simple way to quickly convert from Celsius to Fahrenheit, okay? And I just wanted to share it with you real briefly, just in case this is helpful for you, if you care, okay? But we know that 0 Celsius is 32 Fahrenheit, okay? That's the freezing level for both scales. And we also know that for every 5 that the Celsius goes up, the Fahrenheit goes up 9, okay? So think about it, 0 and 32. Let me put myself back in here for just a second. Let's see here, there we go. So you've got 0 and 32. The 0, the Celsius, is going to go up 5, and the Fahrenheit is going to go up 9, okay? So 0 plus 5 is 5, and 32 plus 9 is 41. So we know that 5 degrees Celsius is 41 degrees Fahrenheit. Now let's do it again. Let's add 5 to 5. Now we get 10. We add 9 to 41. Now we get 50. So we know that 10 degrees Celsius is 50 degrees Fahrenheit. We'll do it one more time. Another 5, 15. Another 9, 59. So 15 Celsius is 59 Fahrenheit. And then if it's in the middle, like say it's 12 Celsius, and you know that 10 is 50 and 15 is 59, then it's in the middle somewhere, like 54, 55. You're going to be within a degree, most certainly. So that's my way of doing it. And of course, it goes the same direction below. Like if you go to minus 5 degrees Celsius, that's going to be 32 minus 9, or 23 Fahrenheit. Minus 10 Celsius is going to be 23 minus 9, or 14. And believe it or not, they meet at minus 40. Okay, they're the same at minus 40. So anyway, I just thought I'd share that with you real quickly. So let me take myself back out here. And so the concept that I wanted to illustrate today really didn't show up very well at either of the North Carolina weather balloon stations. So I found one that did, and that is Little Rock, Arkansas. So this is what their temperature looked like at 7 o'clock this morning, local time. Okay, they're an hour behind us. And you can see this tremendous inversion here, okay, where the temperature starts off just above 50 Fahrenheit, or 10 C, and then it rapidly increases and gets all the way up into the low 60s, about 1,000 feet off the ground, okay? So now And there you can see the labels of that. So a 12-degree increase in about 1,000 feet. So that's a big-time inversion. Now, these are the winds that were observed at those different levels. Now, the straight line here, right there, okay, that tells you the direction the wind is coming from. So this is a south wind, this is a south-southwest wind, and this is a southwest wind. Then the lines that are perpendicular to those lines tell you something about the speed. And the long lines are 10, the short ones are 5. So this would be south at 5. This would be south-southwest at 30, 10, 20, 30. And this is southwest at 35, 10, 20, 30, and then the short one is 5, okay? So up at this 63-degree level, 1,000 feet off the ground, the winds are roaring. Well, not roaring, but I mean, they're a lot stronger than the 5 knots at the surface. So now let's take a look at the observations from the Little Rock station from 7 a.m. to noon. Well, and there's a slight discrepancy here between what was reported at the airport and the upper air station. They're not apparently in exactly the same location. So, but at the airport location, set 49 degrees at 7 o'clock with a calm wind. Then at 8 o'clock, it was up to 53, and the wind was variable in direction at 5 miles per hour. And then it shot up to 62, which is about the temperature at the 1,000 foot above ground level. And now we're starting to pick up a southwest wind, which is exactly what's going on at that higher elevation at 10. And then by the time we get to 9:16, it's southwest at 12, gusting to 22, and it continues to blow between 12 and 15 the rest of the time. Now, it probably would have gotten even stronger, but right in here, it went from basically clear to a solid deck of stratus clouds that was only about 1,000 feet off the ground. And as you can see here, the temperature actually went down a couple of degrees when that happened, and then it started to come back up slowly. So had we not had the development of those clouds, then probably even more of that momentum up there would have mixed its way down to the ground. But certainly you can see the effects that as soon as we got rid of that inversion, we had a definitive wind direction, we had much stronger velocities or speeds, and it really shows this concept very, very clearly, where as soon as you start to mix the air and get rid of the inversion, let me put myself back in here. Let's see here. There we go. As soon as you start to get rid of the inversion, then the air starts to mix over that depth, and not only does some of the warmth begin to mix down, but also the wind speeds at that elevation begin to mix down as well. Not all of it, but at least a part of it. And so that's when your situation will translate into wind gusts that are a little bit higher than the sustained speeds, but even the sustained speeds are significantly stronger than what they are when you're at the bottom of that inversion. So I hope that makes a little bit of sense. So downward transfer of horizontal momentum. The winds are blowing horizontally up here, and as you mix the air over a greater and greater depth, then that horizontal momentum mixes down to the ground, and you start having stronger winds at the surface. Okay, let me click up here. There are the credits. That is the bonus weather video for today. The next one will be coming up on Friday, and of course the next daily weather update coming up tomorrow. So you all have a great Wednesday evening, and we will talk to you again tomorrow. See you later, everybody.